welcome to 19th lecture, and we are discussing one of the very important topics, that is how to solve a differential equation, because differential equations you cannot avoid whenever you want to analyze a circuit in time domain having energy storing elements. So, in our last class I told you we took this general first order differential equation which whose output is y t. So, dy dt plus a y is equal to, on the right hand side there is a forcing function. So, this is input or forcing function, input or forcing function, and y is the output desired, or maybe the current or voltage across a capacitor and so on in circuit analysis. So, this y t is this one, that is the output we are interested in. So, we have formed a differential equation. This is a first order differential equation, first order differential equation. So, we know how to solve it by multiplying with integrating factor and so on, but then we found out that the solution of this equation, total solution, and whenever this differential equation is given, you are also provided with first order differential equation, one boundary condition will be necessary, that is y 0 minus or y 0, that is same as that one for reasonable good function x t. This is given. Okay. The value of y 0 is known. So, the solution will consist of a natural response plus a solution due to forcing function, which I am writing as t. These are the two parts. Now, this natural response alone, if you substitute, that is natural response will be the solution. If the right hand side is 0, then you get y n t, and y n t if you substitute alone on the left hand side, it will always give rise to 0, because d y n dt plus a y n has to be 0, that is why it is the solution. And the question is about this forcing function, and the solution of this one y n t is equal to some constant into e to the power minus a t, that is the thing. Now, at this point I will tell you another important thing, that this equation can be written as a d plus a into y n is equal to 0, where d is this operator d dt. Then if you substitute d by some m, we say that m plus a is equal to 0 is the characteristic equation. Of this one, and the root of the characteristic equation is m equal to minus a. In fact, it is this root which comes as m t. If the root is m, it is equal to a into e to the power m t, and then I have substituted the value of a. Therefore, given a differential equation, characteristic equation can be easily formed, and the root of this equation eventually comes as the coefficient of t in this exponential term. Anyway, so that is the thing. Now, the question is, what should be the nature of y f t? Y f t, nature of y f t, we have seen will be a linear combination of x t, k 1 x, and its higher order derivatives up to infinite terms, that is k1 k2 x dot plus k3 x double dot up to infinity, a linear combination of the forcing function and its higher order derivatives. This will be the nature of y f t. So, the total solution y t then will be a into e to the power minus a t plus of k 1 x plus k 2 x dot plus k 3 x double dot up to infinity. This is the solution, and the point I want to make it now, given the differential equation, I am not going to integrate or things like that. Straight away from this I should be able to write the. So, here the nature of the solution is known, only thing these constants are to be determined. So, how to do that? For example, last time I was trying to doing a problem. Suppose I say that the equation is example. It was like this, that dy dt plus 2y is equal to suppose some t square, and it is given that y 0 is equal to 0, this boundary condition given, boundary condition, and get the total solution of the system. So, the steps will be like this: d dt you replace by m. So, this equation is d dt plus 2 into y is equal to t square. Now, I will say that characteristic equation will be m plus 2 is equal to 0, that is x t is equal to 0, like this, is it? So, root is m equal to minus 2, that is what you get. Then I will say the solution is, total solution is, natural response solution will be a into e to the power minus 2 t plus plus this terms. Now, these terms, although it is infinite, but for this function it will be like this, k 1 into t, k 1 into t square plus k 2 into t, because differentiation is 2 t, 2 will be absorbed in this constant k 2 plus differentiate it once again k 3. After that no terms exist. So, that OD goes, I mean it is like this. So, this is the total solution. Now, after you get the total solution, you have to find out so many constants. See, once you write this, you have solved the 90% of the problem without wasting much time. Only thing you have to find out the characteristic root and say that the nature of the solution will be like this. Now, okay, these constants are to be determined. Now, I told you one thing, that solution due to the forcing function, this point is to be remembered, y f t alone will satisfy the differential equation dy dt plus a y is equal to x t. It has to, because y n part will always give rise to 0. So, it will be, so this one is true. If that is true, then I will say that this part is the forcing function except not except t, y f t. So, y f t alone will satisfy this differential equation. So, I will put it here in the differential equation. And I will say that the differential equation was dy dt plus 2y, it was equal to t square in this case. Forcing function will alone satisfy this. Therefore, y f t we have seen that its nature has to be k 1 t square plus k 2 t plus k 3, only 3 terms. So, put it here. If you put it here, so d dt of y f t will be 2 k 1 into t plus k 2, is not, dy f dt 2 k 1 plus k 2, dt of k 3 vanishes, only 2 terms will be there, okay? And then plus 2 y f. 2 y f is 2 k 1 t square plus 2 k 2 t plus 2 k 3, and that has to be equal to t square. This is the thing. Or you collect the terms, if I make a mistake, point out. So, it will be 2 k 1 t square term. T terms are, what are the t terms? This is 1, this is 1 plus 2 k 1 plus k 2 into t, and plus the constant term, that is 2 k 3 plus k 2, and this I am telling it is t square. Now, this thing has to be true for all time t, no matter what is the time. So, this is an identity. Therefore, coefficients equate the coefficients of t square, t and t to the power 0 on both sides. That is 2 k 1 must be equal to 1. On the right hand side there is t square, here also it is t square. So, its coefficient is 2 k 1, it must be equal to 1. Therefore, it straight away gives you k 1 is equal to half. There is no t terms here. So, coefficient of t terms on the right hand side is 0. So, I will say 2 k 1 plus k 2 is equal to 0, or k 1 plus k 2 is equal to 0. Therefore, I know k 1, k 2 must be equal to minus half, like this. Finally, 2 k 3 plus k 2, constant term there, on the right hand side no constant. So, that is also equal to 0. Therefore, you know 2 k 3 is equal to minus k 2, or 2 k 3 is equal to half, is not, minus half, or k 3 is equal to 1 by 4. Therefore, except t, y f t will be equal to k 1 t square, put the values there. So, k 1 was half t square plus k 2 into t, that is minus half into t plus k 3, which is equal to 1 by 4. This will be the solution due to forcing function, mind you, solution due to forcing function. Therefore, total solution now I know is a into e to the power minus 2 t, that was the natural solution of the system, and plus this thing half t square minus half t plus 1 by 4. To find out this constant, now apply the boundary condition. What is the boundary condition given? Boundary condition, now apply boundary condition to the. So, boundary condition is to be applied to the total solution, mind you. So apply boundary condition, which is given to be y 0 is equal to 0. Therefore, I will say that a at t equal to 0, y 0 is 0. So, put t equal to 0. So, it will give you a, this will give you 0 plus 1 by 4 is equal to 0, because boundary. So, a is equal to minus 1 by 4, and hence finally, I will say that total solution of dy dt plus 2 y is equal to t square with boundary condition y 0 is equal to 0 is y t, which is equal to, I have found out now, a is equal to minus 1 by 4. So, minus 1 by 4 into e to the power minus 2 t, then k 1 t square, k 1 was minus of plus, then k 2 into t minus half t plus plus 1 by 4. This will be the solution. You can verify at t equal to 0, it must give rise to 0, is it? Minus 1 by 4, minus 1 by 4, t equal to 0, it will vanish, and these two terms are already 0, t equal to 0. So, at least it is satisfying, hopefully it is correct. Therefore, you see, to solve the differential equation, at least first order differential equation, it is so easy. This way if you solve, it will give you better insight into the problem, and I am not integrating anything. If I know that rule, that the total solution will be one exponentially decaying term depending upon the characteristic root, and then the rest of the thing is x dot x plus x dot plus x double dot, linear combination of those terms, of course, up to infinity. For example, let us say another example, let us say example 2, dy dt plus say 3 y is equal to 5, a constant DC voltage. Suppose this circuit, RL circuit, you have connected a 5 volt supply to it. Suppose the current in the circuit I am telling y. So, voltage drop, and suppose the value of R is 3 ohm, L is 1 Henry, or I will write it I, why I, let us write I. Anyway, differential equation matters. So, what is the differential equation? Differential equation will be this L di dt suppose L is 1 Henry, 1 into di dt plus Ri, Ri is this, and that is 5. So, it is a first order differential equation and it is in this form di dt plus 3I is equal to 5. We have solved it earlier, but now I will apply this method to solve it very quickly. First thing is characteristic equation. M plus 3 is equal to 0, characteristic root is equal to m equal to minus 3. This is your forcing function, forcing function. So, if you so total solution I t will be equal to a into e to the power minus 3 t, that is, that part is over, plus forcing function, linear combination of forcing function and its higher order derivatives. Higher order derivatives will be 0 because it is constant number 5, d 5 dt is 0, d 2 5 dt 2 is 0. So, only one term will remain here and that will be proportional to 5 plus k 1, you know, x t is 5 into k 1, that is the thing. Then this will be the solution. Okay. And boundary condition given is, suppose I 0 is equal to 0, that is I 0 minus 0, I 0 is 0. So, I will find out the solution here, but one thing is, this is the solution due to forcing function, and forcing function alone will also satisfy this equation. So, I will first find out this k 1 by putting 5 k 1 which is constant, that will be 0 plus 15 k 1 and that is equal to 5, you know, and obviously, here no complications, identity it is. So, k 1 is equal to 1 by 3, 5 by 15, k 1 is over. Therefore, then I will say total solution is equal to a into e to the power minus 3 t plus 5 by 3. This is the solution, total solution. Now, to find out the constant a, apply the boundary condition which is I 0 is equal to 0. So, I 0 equal to 0 will give you what? 0 is equal to a plus 5 by 3 and this is the solution up to this, correct na? K 1 is 5 by 15, 1/3. So, at t equal to 0 it will be a plus 5 by 3, this is the thing. Therefore, a is equal to minus 5 by 3. So, what will be the total solution? I t will be equal to minus 5 by 3, minus 5 by 3 e to the power minus 3 t plus 5 by 3, which is equal to 5 by 3 you take common and 1 minus e to the power minus 3 by t, and it is consistent. RL circuit, final current is 5 by 3 for this circuit, and the time constant is 1/3. So, this is nothing but this is okay, that is all, 1/3 is the time constant. Therefore, you get the same solution very quickly. In case I am telling you one another nice thing about it, if your excitation is constant number, all this you do, that is fine. Further you can reduce your labor, that is if the right hand side is constant, the solution, that is IFT, due to forcing function will be suppress this term, suppress this term di dt, 5/3 will be the thing. Got the point? You suppress di dt term, then solve for I, it is 5/3. In one stroke I could also write that, but anyway this is the most general way. Therefore, I told you how to apply, but once again I am reiterating this point very carefully, that forcing function alone satisfies the differential equation, then it will give rise to an identity. So, equate the coefficients of the like powers on the left hand side and right hand side to get the constants k 1, k 2, k 3, etc. That is one thing. And second thing is, then write down the, so first determine k 1s, forcing function constant, and then you write down the total solution, then apply boundary condition. This is very important step. It is not that you start applying the boundary condition only to the solution due to forcing function. That point should be noted. I hope you have understood this. Now, so far so good. So, what we have seen is this so we have seen that dy dt, at least the first order differential equation A y is equal to x t. It may be voltage, y may be current, and so on. In mechanics, y may be displacement, x may be applied force. Anyway, whatever it is, and boundary condition is given, that is output boundary condition is suppose given, some value it will be given. Okay. It is 0, I am assuming. And I told you, let me write many a time, so that you understand. This solution consists of a natural part plus solution due to forcing function, which will depend on x t alone, and the solution due to natural response you get from the characteristic equation. You find this constant and say that it is a into e to the power minus m t, m is equal to minus a, that is all, plus solution due to forcing function will be k 1 x plus k 2 x dot plus k 3 x double dot, linear combination of x and its higher order derivative. That is the thing. And now I know, okay, with the functions we will be handling in network analysis, this term one need not think one has to differentiate indefinitely to get the solution. Okay, that is there, then you get that. There is one exception, that is why I have written this one. An interesting exception. An interesting exception to this rule. What is that? Suppose I say that differential equation is like this, a y, and the forcing function is e to the power minus a t. See, characteristic root is minus a. If on the right hand side the forcing function is e to the power minus a t, what will be the solution? So, from this it looks like a to the power minus a t, and this I will do, but if you do, you will be making a mistake. Why? I am telling you, because all these equations were found out from fundamental things. What was that fundamental thing? You multiply with integrating factor on both the sides. Is not? We got after all this thing by multiplying with integrating factor starting from the first principle, and here if you multiply this becomes 1. There may be some other constant multiplied here 5 e to the power minus 80, that does not matter. So, this will be the thing. So, what you get here is d dt of e to the power 80 into y is equal to 1. So, what will be e to the power 80 into y? It will be t, because if you differentiate t you get 1, integrate both sides, take dt that side, is not? That is, I have taken this dt to that side and integrated. So, you will get like this and plus a constant, of course, constant of integration. Then your y will be t into e to the power minus 80, multiply both sides with e to the power minus 80 plus a into e to the power minus 80. So, the solution will be a plus t into e to the power minus 80, and this is not the natural part remains undisturbed, but it is not the forcing function, solution due to forcing function is e to the power minus 80, but it will be not like up to infinity you differentiate like that. So, this rule of exception one must understand. Then of course, it will be very easy, you just integrate and get that. Therefore, if the root characteristic root happens the excitation function or input functions happens to be same as the characteristic root e raised to the power same mt, then one has to do like that. Okay, this we just remember, be careful about x t. Okay. Now, so in the first order system things are pretty simple. Now, to complete the discussion on this, we will take up now higher order differential equation and try to see that whether similar things can be done. That is, suppose a higher order differential equation is like this plus a dy dt plus by, it is a second order differential equation and it is excited by input output. Whether by inspection looking at this differential equation, whether can I write y t, the nature of y t in the same way as I have done in case of a first order system. So, in the next class I will be doing that. Thank you.